Picture this, an invisible sculptor at work in the depths of space, chiseling delicate patterns into vast rings of ice and dust, crafting masterpieces so immense they could span continents, yet hidden in plain sight. These aren't the creations of some cosmic artist, but the handiwork of something even more extraordinary: cosmic storms. Yes, storms, but not the kind that bring rain or thunder. These are celestial tempests, swirling through planetary rings with the force of gravity and magnetism, carving gaps, spirals, and waves into what we once thought were simple, static bands of debris. And here's the thing: you've probably seen Saturn's rings shimmering in telescope images, but what you haven't seen are the invisible sculptures being shaped right now by these storms, hidden just beyond our sight. This is where the universe reveals its flair for drama. Planetary rings aren't just pretty accessories, they're dynamic, ever-changing stages where chaos and order dance together. Cosmic storms erupt without warning, sculpting the rings into intricate formations that defy our expectations. Some of these disturbances last for centuries, while others vanish in days, leaving behind only faint traces of their existence. And the most astonishing part, we're only just beginning to decode their secrets. For decades, we assumed rings were orderly, predictable systems. But thanks to spacecraft like Cassini, we now know they're alive with motion, shaped by forces we're still learning to measure. So how does something as intangible as a storm leave its mark on a planetary ring? That's the mystery we're diving into today. From the gravitational tugs of hidden moons to the invisible push of magnetic fields, these storms are rewriting the rules of celestial mechanics. They create spirals that rival galaxies in elegance, gaps so precise they look machine-cut, and ripples that stretch for thousands of miles, all while remaining invisible to the naked eye. This isn't just science, it's art on a cosmic scale, a reminder that the universe has a way of blending beauty and physics in ways we're only starting to grasp. So let's embark on this journey together, peeling back the layers of these invisible sculptures to uncover the forces that shape them and what they tell us about the hidden workings of our solar system. Planetary rings might look like smooth, serene halos from a distance, but up close, they're anything but tranquil. Think of them as vast cosmic construction sites where countless particles, some as tiny as grains of sand, others as large as boulders, are constantly jostling, colliding, and rearranging themselves. These rings aren't just floating there, they're alive with motion, governed by an intricate dance of forces that keep them in a state of perpetual change. Gravity is the primary architect here, pulling everything toward the planet's center while also tugging material into orbit, but it's not acting alone. Electromagnetic forces come into play, especially when charged particles interact with the planet's magnetic field, creating subtle but powerful currents that can push and pull the ring material in unexpected ways. Then there's the role of collisions, which might sound destructive but are actually essential to the ring's structure. When particles smash into each other, they can stick together or break apart, forming new configurations that ripple through the system. This constant reshuffling creates a delicate equilibrium, where the rings maintain their shape even as individual particles are always on the move. It's a bit like a crowded dance floor where everyone is constantly switching partners, yet the overall pattern stays intact. Moons orbiting nearby add another layer of complexity. Their gravity acts like a sculptor's chisel, carving out gaps and waves in the rings. Some moons, like Saturn's Prometheus, even plow through the ring material, creating ripples that can spiral outward for hundreds of miles. These interactions are so precise that scientists can use them to predict where new features will form, almost like reading the ring's fingerprints. And let's not forget the smaller, hidden moonlets, tiny worlds embedded within the rings themselves, whose gravity can create propeller-shaped disturbances that fan out like miniature whirlpools. What makes planetary rings so fascinating to scientists isn't just their beauty, but what they reveal about the early solar system. These rings are like cosmic time capsules, preserving conditions similar to those in the protoplanetary disk that once surrounded our young sun. By studying how particles clump together or disperse in the rings, researchers can piece together how planets might have formed from similar disks of gas and dust billions of years ago. It's a window into our own origins, written in the language of ice and rock. But perhaps the most surprising thing about planetary rings is how fragile they are. Despite their grandeur, they're incredibly sensitive to disturbances. A passing comet or a shift in the planet's magnetic field can trigger cascading effects, altering the ring's structure in ways that take centuries to settle. This delicate balance between order and chaos is what sets the stage for the cosmic storms we'll explore next, tempests that shape the rings in ways we're only beginning to understand. Cosmic storms are nothing like the thunderstorms or hurricanes we experience on Earth. Instead of wind and rain, these celestial tempests are fueled by invisible forces, gravity, magnetism, and the relentless motion of charged particles. Picture a vast ocean of ice and dust stretching thousands of miles across, where waves rise not from water but from the subtle tug of a moon's gravity or the crackle of electric currents. These storms don't rage with sound and fury. They unfold in near silence, their power measured in the delicate rearrangements of ring material over centuries. What makes them so fascinating is their scale and subtlety. A single cosmic storm can carve out gaps as wide as continents, spiral arms that mirror miniature galaxies, or ripples that propagate like echoes through the rings. Yet, despite their grandeur, they're invisible to ordinary telescopes. Scientists detect them indirectly, using radio waves to map disturbances or infrared sensors to catch the faint heat signatures of colliding particles. It's like listening to a symphony played in the dark. We can't see the instruments, but the patterns they create reveal the music of the cosmos. The driving forces behind these storms are as varied as their effects. Sometimes it's the gravitational pull of a nearby moon, stirring the ring material like a spoon in coffee, creating waves that spiral outward. Other times, charged particles energized by a planet's magnetic field collide with ring debris, triggering cascades of motion. These interactions can snowball into sprawling disturbances, reshaping entire sections of the rings in ways that persist for generations. Unlike Earth's weather, which changes by the hour, cosmic storms unfold over decades or even centuries. A single ripple in Saturn's rings might have begun its journey before telescopes were invented, slowly spreading like a whisper across the void. This slow-motion chaos challenges our understanding of stability in space. We often think of planetary rings as timeless, but they're more like living tapestries, constantly rewoven by forces we're only beginning to decipher. The transient nature of these storms adds to their mystery. Some vanish as quickly as they form, leaving behind only faint scars in the ring structure. Others linger, their signatures etched into the rings like ancient hieroglyphs waiting to be decoded. By studying them, scientists aren't just uncovering the secrets of planetary rings. They're piecing together a universal language of motion, matter, and energy that shapes everything from asteroids to galaxies. And the more we learn, the clearer it becomes. These invisible storms are the sculptors of the solar system, quietly shaping the beauty we see from afar. Hidden beneath the serene beauty of planetary rings lies an invisible force shaping their destiny, the magnetosphere. Picture a colossal, invisible web of magnetic fields stretching far beyond the planet itself, a dynamic shield that does far more than deflect solar wind. For ring systems, this magnetic environment acts like a cosmic conductor, orchestrating the movement of charged particles with breathtaking precision. Saturn's magnetosphere, the second largest in our solar system after Jupiter's, is a powerhouse of activity. It funnels electrons and ions into the rings, where they collide with icy fragments, creating sparks of energy that ripple through the structure. These interactions are anything but random. They follow the magnetic field lines like highways, tracing intricate paths that scientists can map using radio emissions. The real magic happens when these charged particles meet the ring material. Imagine sprinkling iron filings near a magnet. The way they align along the field lines gives a hint of the invisible forces at work. In Saturn's rings, something similar occurs, but on a scale so vast it defies imagination. Electric currents surge through the rings, generated by the dance between magnetic fields and charged dust. These currents can trigger localized turbulence, stirring up mini-storms that sculpt the rings from within. Some of these disturbances manifest as dark streaks or bright patches, visible only to instruments sensitive to their unique signatures. Auroras aren't just an earthly phenomenon. Saturn's rings have their own version, glowing faintly where charged particles excite the thin gas between ring particles. These ethereal lights are more than just a spectacle. They're clues to the energy flowing through the system. By studying them, researchers have discovered that the magnetosphere doesn't just passively influence the rings, it actively reshapes them. During periods of heightened solar activity, surges of charged particles bombard the rings, amplifying storms and leaving behind patterns that can last for decades. What makes these magnetic interactions so pivotal is their universality. The same processes likely occur around Jupiter, Uranus, and Neptune, each with its own unique twist. Jupiter's stronger magnetic field, for example, accelerates particles to higher energies, creating more intense storms in its faint rings. Even exoplanets with ring systems probably experience these phenomena, suggesting that magnetospheres could be key architects of ring structures across the galaxy. Unraveling these mysteries isn't just about understanding Saturn or Jupiter. It's about decoding a fundamental language of the cosmos. Magnetic fields govern everything from star formation to galaxy evolution, and planetary rings offer a rare, close-up view of these forces in action. Every ripple, every surge of current is a piece of a puzzle that stretches far beyond our solar system, revealing how the universe sculpts its grandest designs with invisible hands. Moons orbiting near planetary rings aren't just passive bystanders, they're master sculptors. Their gravity chiseling intricate patterns into the surrounding debris like celestial artists at work. Take Saturn's moon Daphne's, barely 5 miles across, yet its gravitational pull carves a crisp 30-mile gap in the rings called the Keeler Gap. As Daphne's orbits, its gravity tugs on nearby ring particles, creating ripples along the gap's edges that resemble the wake of a boat gliding through water. These disturbances aren't fleeting. They're etched into the rings for centuries, a testament to the enduring influence of even the smallest moons. But the real marvel lies in the way these gravitational interactions can snowball into full-blown cosmic storms. When a moon's gravity resonates with the orbital rhythm of ring particles like a pendulum swinging in perfect sync, it can amplify tiny disturbances into sprawling spiral waves. Saturn's moon Mimas, for instance, creates the colossal two-lobed division known as the Cassini Gap, but its influence doesn't stop there. Its gravitational nudges also generate spiral density waves that coil outward through the rings like the grooves of a vinyl record, each one a frozen snapshot of the moon's relentless sculpting. Enceladus offers perhaps the most dramatic example of this moon ring ballet. This icy moon doesn't just shape the rings with gravity, it actively feeds them. Geysers near its south pole blast water vapor and ice crystals into space, a portion of which settles into Saturn's outermost E-ring. Meanwhile, Enceladus's gravity herds these particles into subtle arcs and clumps, creating a dynamic, ever-changing structure. It's a two-way street. The moon supplies the material, then molds it with invisible gravitational hands. The dance between moons and rings isn't always graceful. Some moons, like Prometheus, plow through ring material like a snowplow, kicking up chaotic ripples and knots. Others, like Pan, orbit so close to the rings they've carved out their own paths, their gravity scooping up debris to form peculiar, saucer-shaped waves. These interactions reveal a hidden truth. Planetary rings are anything but static. They're battlegrounds of competing forces, where moons of all sizes leave their mark, from feathery ripples to gaping chasms. What makes these gravitational sculptures so valuable to scientists is their predictability. Unlike the chaotic turbulence of cosmic storms, moon-induced patterns follow precise mathematical rhythms. By studying them, researchers can reverse engineer the mass and orbit of unseen moons, or even uncover clues about the ring's age and composition. Every ripple, every gap is a breadcrumb leading back to the forces that shaped it, a celestial detective story written in gravity's invisible ink. And here's the kicker: these processes aren't unique to Saturn. Jupiter's faint rings bear the scars of its own moons, while Uranus's tilted rings showcase bizarre, jagged edges shaped by undiscovered satellites. Even exoplanets likely host similar moon ring symphonies, waiting to be observed. The lesson is clear: where there are rings, there are moons shaping them, their gravitational whispers transforming chaos into art on a scale we're only beginning to appreciate. Spiral density waves are one of the universe's most elegant demonstrations of order, emerging from chaos, celestial fingerprints pressed into the fabric of planetary rings. Picture the grooves of a vinyl record, but instead of music, these spirals tell the story of gravitational whispers between moons and ring particles. They form when a moon's orbit syncs up perfectly with the motion of ring material, creating a rhythmic push and pull that sends ripples cascading outward. It's like a child on a swing. Give a gentle push at just the right moment, and the swing goes higher with each cycle. In Saturn's rings, moons like Mimas and Janus act as those careful pushers, their gravity nudging particles into synchronized waves that can stretch for thousands of miles. What's astonishing is how these waves preserve history. A single spiral might have been triggered centuries ago by a moon's passing, its pattern frozen in time like a snapshot. Scientists can read these waves like tree rings, decoding their spacing and shape to uncover details about the moon's mass, the ring's composition, even the temperature of the particles when the wave first formed. Some spirals are so tightly wound they resemble the arms of miniature galaxies, while others fan out like the delicate folds of a seashell. Their precision isn't accidental, it's a direct reflection of the mathematical harmony governing celestial motion. The waves also reveal hidden forces at play. Charged particles within the rings interact with magnetic fields, adding subtle twists to the spirals that wouldn't exist from gravity alone. In Saturn's B ring, for example, electromagnetic effects warp the waves into faint, jagged edges, a reminder that these structures are more than just gravitational artifacts. They're dynamic sculptures shaped by an invisible orchestra of forces. What makes spiral density waves so captivating isn't just their beauty, it's their universality. Similar patterns appear in protoplanetary disks around young stars, where gravity and rotation conspire to create waves that may seed planet formation. By studying Saturn's rings, we're glimpsing processes that shape entire solar systems, a cosmic connect the dots linking the tiniest ring particles to the birth of worlds. And just like a stone tossed into a pond, the ripples from these discoveries extend far beyond our own celestial backyard. Nestled within Saturn's dazzling rings, the Keeler Gap is a masterpiece of celestial engineering, a razor-thin void just 26 miles wide, carved and maintained by a moon no larger than a city. Daphnis, the unassuming shepherd moon responsible for this precision, weighs in at a mere 5 miles across, yet its gravitational influence punches far above its size. As it glides through the gap, Daphnis tugs on nearby ring particles like an invisible puppeteer, sending ripples cascading along the edges in a mesmerizing display of orbital choreography. These ripples aren't random, they rise in orderly peaks, some towering as high as half a mile, their steep faces sculpted by the moon's relentless pull. From a distance, the gap's edges appear scalloped, as if some cosmic comb had raked through the rings, leaving behind undulating waves frozen in time. But Daphnis doesn't just create static patterns, it stirs up chaos. Occasionally, its gravitational nudges grow powerful enough to destabilize the surrounding ring material, triggering localized storms. Picture a stone dropped into a pond, but instead of water, the ripples are made of ice and dust, fanning outward in intricate spirals before collapsing back into disorder. These tempests are fleeting, lasting days or weeks, yet they leave behind telltale scars, twisted knots of debris, temporary clumps, or even faint grooves etched into the ring plane. It's a delicate balance. Daphnis herds the particles, but sometimes they push back, revealing the dynamic tension between order and turbulence. Shepherd moons like Daphnis are the unsung architects of ring systems. Their role isn't just decorative, they're custodians, using gravity to corral stray particles and sharpen the edges of gaps that might otherwise blur into oblivion. Without them, Saturn's rings would lose their crisp divisions, dissolving into a homogeneous haze. What's astonishing is how efficient they are. Pan, another shepherd moon, orbits so close to the rings that it's gathered a skirt of ring material around its equator, creating a bizarre flying saucer shape. These moons don't just shape the rings, they wear their influence like a badge, their very forms altered by the debris they govern. The Keeler Gap offers more than just a pretty spectacle, it's a laboratory for understanding gravitational resonance. Daphnis orbits in perfect sync with the gap's edges, its gravitational kicks arriving at just the right interval to reinforce the ripples rather than dampen them. This synchronization is so precise that scientists can use the waves to calculate the moon's mass and density, turning the gap into a celestial scale. And there's a deeper lesson here. Across the universe, from galaxies to atom clouds, resonance is a universal sculptor, shaping structures great and small through the same harmonic principles at work in Saturn's rings. What makes shepherd moons truly remarkable is their humility. They're not the largest or brightest objects in the solar system, but their influence is disproportionate. A moon like Daphnis might weigh 1 billion times less than Saturn, yet it commands a swath of rings thousands of times its own size. It's a reminder that in the cosmos, size isn't everything. Gravity's reach is infinite, and even the tiniest worlds can leave the grandest marks. As we peer deeper into the Keeler Gap, we're not just seeing a moon and its ripples, we're witnessing the universe's quiet genius for turning chaos into art, one gravitational nudge at a time. While gravity gets much of the credit for shaping planetary rings, there's another invisible artist at work, the subtle but relentless push and pull of electromagnetic forces. Picture this: trillions of tiny ice particles, each one bathed in the glow of charged particles streaming from the planet's magnetosphere. these particles don't just float passively, they become actors in an invisible cosmic theater, where magnetic fields direct their motions like an unseen hand. Saturn's rings, for example, are constantly bombarded by electrons and ions trapped in the planet's powerful magnetic field. When these charged particles collide with ring material, they transfer energy, creating faint electric currents that ripple through the rings like whispers in the dark. These electromagnetic interactions leave behind fingerprints that spacecraft like Cassini have learned to read. Dark bands appear where charged particles have stripped away fine dust, leaving coarser grains behind. Bright streaks flare up where currents excite the ice, causing it to glow faintly in radio wavelengths. Some of the most striking features are the so-called spokes, ghostly radial formations that appear and vanish across Saturn's B-ring like brushstrokes on a celestial canvas. Scientists believe these spokes are caused by tiny dust particles levitating above the ring plane, lifted by electrostatic forces as the planet's magnetic field interacts with sunlight. It's a delicate dance of attraction and repulsion happening on scales both vast and microscopic. What makes these forces so fascinating is their unpredictability. Unlike gravity, which follows precise orbital mechanics, electromagnetic disturbances can flare up suddenly, triggered by solar storms or shifts in the planet's magnetosphere. During these events, the rings become a battleground of competing forces: gravity, trying to hold particles in orbit while electromagnetic turbulence pushes them into new configurations. The result: temporary whirlpools of debris, swirling currents of charged ice, and even lightning-like discharges crackling through the rings. Yet amidst this chaos, patterns emerge. Saturn's F-ring, for instance, showcases braided strands and kinked loops shaped by the interplay of magnetic fields and nearby moonlets. These structures aren't static, they evolve in real time, offering scientists a front-row seat to the dynamic processes that shape ring systems. And it's not just Saturn. Jupiter's faint rings also bear the marks of electromagnetic sculpting, with glowing halos of dust extending along the planet's magnetic equator. The deeper we look, the clearer it becomes. Electromagnetic forces are the unsung architects of planetary rings. They may not carve gaps as dramatically as moons do, but their influence is everywhere, subtle, persistent, and utterly transformative. By studying these interactions, we're not just decoding the secrets of Saturn or Jupiter, we're uncovering universal principles that likely govern ring systems around distant stars, where similar invisible hands are at work, shaping cosmic masterpieces we've yet to discover. Among the countless wonders hidden within Saturn's rings, few are as enigmatic as the propeller. Features tiny, wing-shaped disturbances that appear and vanish like ghostly imprints. These delicate formations, some no larger than a football field, are the handiwork of unseen moonlets, miniature worlds only a few hundred feet across, lurking within the ring material itself. Too small to carve out full-fledged gaps like their larger moon cousins, these moonlets instead leave behind fleeting trails, their gravity pushing ring particles aside as they orbit, creating symmetrical ripples that resemble the blades of an airplane propeller. What makes these features so intriguing is their transient nature. Unlike the grand spiral waves or gap edges shaped by larger moons, propellers are ephemeral, often lasting just weeks or months before the relentless motion of the ring particles smears them back into uniformity. Yet in their brief existence, they offer scientists a rare glimpse into the hidden population of moonlets, objects too small to spot directly, but whose presence is betrayed by the disturbances they leave behind. The Cassini spacecraft, during its mission, catalogued thousands of these propellers, each one a clue to the unseen architecture of the rings. Some, like the one whimsically named Blériot after a pioneering aviator, spanned nearly 20 miles, their twin lobes stretching outward like wings frozen in motion. The mechanics behind these formations are deceptively simple yet reveal profound truths about ring dynamics. As a moonlet orbits within the rings, its gravity creates a zone of influence around it, repelling nearby particles. The result is a pair of gaps, one slightly ahead of the moonlet, one slightly behind, flanked by regions where particles pile up, forming the characteristic propeller shape. It's a miniature version of the process that creates grand gaps like the Keeler division, scaled down to a size that highlights the delicate balance of forces at play. But propellers aren't just cosmic curiosities, they're time capsules. By studying their size and shape, researchers can estimate the mass of the moonlets that create them, offering hints about the population of these hidden builders. Some propellers suggest the presence of moonlets as small as a house, while others hint at objects closer in size to a skyscraper. Their distribution tells another story. Propellers are far more common in Saturn's A ring than in the denser B ring, suggesting that moonlets either form more readily there or survive longer in the less chaotic environment. Perhaps the most astonishing insight from these tiny features is their role in the ring's evolution. Moonlets aren't just passive residents, they're active participants, their gravity stirring the ring material, redistributing debris, and even seeding the formation of larger structures. Some scientists theorize that propellers could be the early stages of moon formation, where a small clump of material gradually grows by sweeping up surrounding particles. If true, these unassuming features might represent the birth cries of future moons, frozen in the act of becoming. The study of propellers also bridges the gap between planetary rings and other astrophysical disks. Similar processes likely occur in the protoplanetary disks around young stars, where tiny clumps of dust and gas could be sculpting their own versions of propellers' early steps toward planet formation. By decoding the physics of Saturn's propellers, we're not just unraveling the secrets of a single planet's rings, we're peering into the universal mechanisms that shape celestial structures across the cosmos. Yet for all we've learned, propellers retain an air of mystery. Why do some moonlets create long-lived, symmetrical propellers while others leave behind only chaotic smudges? How do these tiny objects avoid being shattered by collisions in the densely packed rings? Each new observation peels back another layer, revealing a world where even the smallest players wield outsized influence, sculpting the rings in ways we're only beginning to comprehend. And as we continue to study these fleeting signatures, one thing becomes clear. In the grand tapestry of Saturn's rings, even the tiniest threads hold cosmic significance. Saturn's rings shimmer with an ethereal glow, but what few realize is that they're slowly vanishing one particle at a time. This gradual disappearance, known as ring rain, is one of the solar system's most understated dramas. Imagine tiny ice crystals, some no larger than dust grains, becoming electrically charged by sunlight or collisions, then caught in the planet's magnetic grip like iron filings drawn to a magnet. Instead of orbiting endlessly, these particles spiral inward, tracing magnetic field lines down into Saturn's upper atmosphere, where they burn up in a silent, perpetual shower. It's a loss so subtle that human eyes would never notice, yet over millions of years, it could drain entire ring systems dry. What makes ring rain so fascinating isn't just its inevitability, it's the way cosmic storms supercharge the process. During turbulent periods, waves of charged particles surge through the rings, knocking more debris loose and funneling it toward the planet. Think of it like a tree shedding leaves in a storm. The heavier the turbulence, the faster the material falls. The Cassini spacecraft detected this firsthand when it flew through the gap between Saturn and its rings, measuring a surprising downpour of ice and organic compounds raining into the planet's equator. Some estimates suggest the rings lose enough water every second to fill an Olympic-sized swimming pool, a staggering rate that hints at their ephemeral nature. But here's the twist: ring rain isn't uniform. Saturn's magnetic field is tilted, creating hotspots where particles funnel down more intensely, like water swirling around a drain. These uneven losses could explain why some rings appear brighter or darker over time, their composition shifting as lighter particles vanish faster than heavier ones. The B ring, for instance, seems to be shedding material more rapidly than the others, a discrepancy that puzzles scientists. Is it because of its density, its particle size, or some hidden interaction with Saturn's magnetosphere? The answers could rewrite our understanding of how ring systems age. The implications stretch far beyond Saturn. If ring rain is common, it might explain why older planets like Uranus and Neptune have such faint, dusty rings their once vibrant systems could have weathered away over billions of years. Even exoplanets with rings might follow the same fate, their majestic halos destined to fade as their material trickles into the void. This raises a profound question. Are we witnessing the rings in their prime, or catching them in the final act of a cosmic performance that's been unfolding since the dawn of the solar system? Yet for all its destructive potential, ring rain also breathes life into Saturn's atmosphere. The infalling particles bring water and complex molecules, seeding chemical reactions that alter the planet's upper layers. Some researchers speculate this drizzle could even influence Saturn's weather, adding moisture to storms or altering atmospheric currents. It's a reminder that in space, nothing truly disappears, it just transforms, becoming part of a grander cycle. The study of ring rain isn't just about predicting when Saturn's rings will fade. It's a window into the dynamic interplay between planets and their surroundings. Every falling particle carries a story, a clue about the forces that shape not just rings, but the evolution of entire planetary systems. And as we piece together these clues, we're left with a humbling truth. Even the most majestic structures in the cosmos are fleeting, sculpted by time and tied on a scale beyond human reckoning. Saturn's rings don't just orbit the planet, they live by its seasons, shifting and transforming as the giant world tilts on its axis over its 30-year journey around the Sun. Picture Earth's seasons but stretched across decades, where a single winter or summer lasts longer than most human missions to study them. This slow celestial ballet has a profound effect on the rings, altering everything from their temperature to the frequency and intensity of cosmic storms. When Saturn's northern hemisphere leans toward the Sun, the rings bask in its light, warming slightly and stirring up electrostatic activity that can trigger storms. During the long polar night, the rings cool, their particles contracting and settling into quieter, more stable configurations. But it's not just about temperature. The angle of sunlight also changes how we see the rings from Earth, revealing hidden structures that vanish when viewed from a different perspective. One of the most dramatic seasonal shifts occurs in Saturn's spoke features, those ghostly radial streaks that appear and disappear across the B ring. These enigmatic formations seem to favor the planet's equinoxes, when sunlight strikes the ring's edge on. Scientists suspect the low angle of light during these periods alters the electrostatic environment, allowing tiny dust particles to levitate and form the spokes. It's a fleeting phenomenon, like frost patterns that only appear on certain winter mornings, and studying it offers clues about how charged particles behave in the ring's unique microgravity environment. The spokes aren't just seasonal quirks, they're windows into the invisible forces that govern ring dynamics year-round. Seasonal changes also influence the ring's broader storm activity. During Saturn's southern summer, for instance, the planet's magnetosphere becomes more active, funneling additional charged particles into the rings. This influx can destabilize ring material, sparking waves of turbulence that ripple outward like weather fronts. Some storms fade as the seasons turn, while others leave permanent scars, spiral density waves that persist long after the conditions that created them have passed. These waves become frozen records of past storms, their spacing and shape encoding details about the ring's viscosity and the forces that shaped them. The ring's response to seasons isn't uniform. Saturn's a ring with its relatively sparse particle density reacts more dramatically to temperature shifts than the densely packed B ring. In the A ring, seasonal warming can loosen the bonds between particles, making them more susceptible to disturbances. The result, a surge in propeller features and mini-storms during warmer periods, as if the ring itself were breathing, expanding and contracting with the planet's slow celestial rhythm. Meanwhile, the Cassini division, the dark gap between the A and B rings, shows almost no seasonal variation, a testament to its unique stability amid the chaos. What makes these seasonal patterns so valuable to scientists is their predictability. Unlike the chaotic turbulence of spontaneous storms, seasonal changes follow a timetable, allowing researchers to prepare observations and test hypotheses. When Cassini witnessed Saturn's 2009 equinox, it captured data that revolutionized our understanding of ring dynamics, from the sudden appearance of towering vertical structures to the temporary brightening of certain regions. These events weren't random, they were part of a cycle, one that repeats every 15 Earth years, offering new opportunities to decode the ring's secrets. The lesson of Saturn's seasons extends beyond our solar system. Exoplanets with ring systems likely experience their own versions of these cyclical changes, influenced by their host stars and axial tilts. Could a giant exoplanet's rings flare with storm activity during its long summers, or grow quiescent in the cold of extended winters? The answer might lie in the patterns we've observed at home, where even the slowest turns of a planet's axis can unleash or quiet the invisible tempests that shape its rings. And as we continue to study these seasonal shifts, we're reminded that time itself is a sculptor, carving its signature into the fabric of the cosmos with the patience of orbits and the precision of gravity. Cosmic dust might seem insignificant compared to the vast ice boulders and glittering debris of planetary rings, but these tiny particles wield surprising influence over the ring's most dramatic storms. Picture grains no larger than smoke particles, each one buzzing with electric charge as sunlight bathes them or magnetic fields sweep past. Individually, they're harmless, but collectively, they become agents of chaos. When charged dust particles collide, they can stick together through electrostatic forces, forming fragile clumps that act like sails, catching the push of sunlight or the tug of magnetic fields. These clumps don't last long. Collisions or tidal forces tear them apart, but their brief existence stirs the ring material, creating ripples of turbulence that can cascade into full-blown storms. The real magic happens when dust interacts with a planet's magnetosphere. On Saturn, for example, charged dust particles spiral along magnetic field lines, gathering into transient clouds that glow faintly in ultraviolet light. These clouds aren't just passive observers, they're active participants in ring dynamics. When they grow dense enough, their collective charge can distort the local magnetic environment, triggering instability. It's like a crowd surging at a concert. The movement of a few can jostle the entire group, leading to unpredictable waves of motion. Some of these disturbances eject dust entirely, lofting it high above the ring plane where it forms wispy, temporary structures before drifting back down or escaping into space. Dust storms in planetary rings aren't just smaller versions of the grand cosmic tempests we've discussed. They operate by their own unique rules. Unlike gravity-driven waves or moon-carved gaps, dust-driven storms are fleeting and hyper-local, often vanishing as quickly as they form. Yet their impact lingers. The Cassini spacecraft spotted dust streaks in Saturn's D-ring, where clusters of particles erupted outward like geysers, leaving behind faint trails that dissolved within hours. These microstorms might not reshape the rings permanently, but they're a constant reminder of the restless energy simmering beneath the surface. What makes cosmic dust so pivotal is its dual nature. It's both a product of ring activity and a catalyst for more. Collisions between larger ring particles constantly replenish the dust supply, while electrostatic forces and radiation pressure ensure it never settles into complacency. In Jupiter's Gossamer rings, for instance, dust ejected by micrometeoroid impacts on nearby moons migrates inward, spiraling toward the planet under the influence of electromagnetic drag. Along the way, it collides with other particles, spawning intricate patterns of light and shadow that shift with the planet's rotation. The study of cosmic dust isn't just about understanding rings, it's a gateway to broader astrophysical mysteries. Similar processes occur in protoplanetary disks, where dust grains clump together to form the building blocks of planets. By observing how dust behaves in Saturn's rings, scientists gain insights into how microscopic particles can snowball into worlds. It's a humbling thought. The same forces that sculpt faint, temporary storms in planetary rings might have once shaped the very ground beneath our feet. Yet for all its importance, cosmic dust remains elusive. Its particles are too small to see directly, and their behavior is notoriously hard to predict. One moment they're drifting peacefully, the next they're at the heart of a storm. This unpredictability makes dust one of the most exciting frontiers in ring science, a reminder that even the tiniest components of the cosmos can hold the keys to its grandest designs. Jupiter's rings might not win any beauty contests next to Saturn's iconic bands, but their subtle elegance hides a universe of complexity, where Saturn's rings blaze with sunlight reflected off countless ice crystals. Jupiter's are ghostly, composed mostly of dark dust particles so fine they resemble smoke. This difference isn't just cosmetic, it's a direct result of their origins. Saturn's rings likely formed from the shattered remains of a moon or comet, leaving behind icy debris that sparkles like crushed diamonds. Jupiter's rings, on the other hand, are fed by constant micrometeoroid impacts on its small inner moons like Amalthea and Thebe. Every collision kicks up clouds of dust, which slowly spiral inward, painting the rings with a muted, rusty hue. The storms that ripple through these two systems couldn't be more different. Saturn's cosmic tempests are grand spectacle spiral waves that unwind like celestial clockwork, or gaps carved by moons with surgical precision. Jupiter's storms, by contrast, are whispers. Without large ice particles to amplify disturbances, its dust rings respond to turbulence in subtler ways. Charged particles from Jupiter's ferocious magnetosphere bombard the rings, electrifying the dust and pushing it into faint, transient ripples. These disturbances lack the dramatic scale of Saturn's formations, but they're no less fascinating. Some scientists compare Jupiter's ring dynamics to a wind-blown desert, where Saturn's rings are glaciers. Jupiter's are shifting sands, reshaping under forces that leave no permanent marks. Uranus adds another twist to the story. Its rings are dark as charcoal, yet they gleam with sharp edges like razor-thin grooves on a vinyl record. Unlike Saturn or Jupiter, Uranus orbits the Sun tilted almost sideways, and this extreme axial tilt bends its rings into strange, off-kilter shapes. Cosmic storms here are rare but intense, triggered when the planet's irregular magnetic field, itself offset from the center, interacts with ring particles. The result, jagged, asymmetrical waves that look like cracks in glass, frozen mid-propagation. even Neptune's rings defy expectations. Its faint arcs, named Courage and Liberté, bunch up like beads on a string, held in place by the gravitational nudges of small shepherd moons. Storms in these arcs are fleeting, often dissolving before telescopes can capture them in detail. What unites these diverse systems is the universal language of physics. Whether it's Saturn's icy waves or Jupiter's dusty ripples, the same forces, gravity, electromagnetism, and collision dynamics, orchestrate each ring's unique ballet. By comparing them, scientists have uncovered a startling truth. A planet's rings are a mirror of its soul. Saturn's grandeur reflects its massive, complex system of moons and magnetic fields. Jupiter's faint rings hint at the relentless bombardment its inner moons endure. Uranus and Neptune, with their offbeat tilts and irregular fields, wear their quirks openly in their ring structures. Yet mysteries remain. Why does Saturn alone boast such dazzling ice-dominated rings? Could Jupiter have once had brighter rings that faded over time? The answers might lie in the delicate balance between creation and destruction. How quickly moons replenish ring material versus how fast storms and ring rain erode it. Every planetary ring is a snapshot of this equilibrium, a fleeting moment in a cosmic dance that's been unfolding for billions of years. And as we study these variations, we're not just cataloging differences, we're piecing together the story of how all planetary systems evolve, one invisible storm at a time. The Sun may be 93 million miles away from Saturn, but its influence reaches far beyond the inner planets, shaping the delicate balance of planetary rings with an invisible hand. Solar wind, a relentless torrent of charged particles streaming outward at nearly 1 million miles per hour, doesn't just create auroras on Earth. It stirs up invisible tempests in the rings of gas giants. When these high-energy particles collide with ring material, they don't just bounce off harmlessly. They electrify the ice and dust, altering their behavior in ways that can trigger storms lasting for months or even years. One of the most dramatic effects of solar wind is its ability to brighten or darken sections of the rings, almost like a celestial dimmer switch. Charged particles from the Sun can strip electrons from icy ring fragments, causing them to emit faint glows in ultraviolet light, a phenomenon Cassini observed during Saturn's equinox. Conversely, in other regions, solar wind bombardment can darken ring material by eroding surface ice, leaving behind a patina of dust that absorbs more sunlight. These changes aren't just cosmetic, they influence the ring's temperature, which in turn affects how particles clump together or disperse, setting the stage for turbulence. During periods of heightened solar activity like solar flares or coronal mass ejections, the rings become a cosmic weather vane, reacting to the Sun's outbursts with surges of storm activity. Imagine a pebble tossed into a pond, but instead of water, the ripples are made of charged particles cascading through the rings, destabilizing delicate structures. In 2012, astronomers witnessed a massive solar storm buffet Saturn's rings, triggering waves of electrostatic activity that propagated like dominoes through the B-ring. These disturbances didn't carve permanent scars, but they left behind temporary ripples and kinks, evidence of the Sun's fleeting yet powerful touch. What makes solar winds roll so fascinating is its duality. On one hand, it's a destructive force, eroding ring material over millennia. On the other, it's a creative one, shaping dynamic features that wouldn't exist without its influence. The faint radial spokes in Saturn's B-ring, for example, are thought to form when solar wind charges tiny dust particles, levitating them above the ring plane like iron filings on a magnet. These spokes appear and vanish with the rhythm of Saturn's rotation and the Sun's activity, a reminder that even the most distant star can choreograph motion in the cosmic dance. Yet solar wind doesn't act alone. It teams up with a planet's magnetic field, amplifying or dampening its effects. At Jupiter, where the magnetic field is 20,000 times stronger than Earth's, solar wind particles are funneled into the rings with devastating energy, creating auroras within the ring plane itself. Uranus, with its bizarre sideways magnetic field, experiences solar wind in bursts, its rings lighting up unevenly as charged particles surge along skewed field lines. These variations reveal a universal truth: no two ring systems weather the solar storm alike. The deeper we look, the clearer it becomes that the Sun is more than just a bystander in the life of planetary rings. It's a sculptor, a disruptor, and a silent partner in their evolution. Every gust of solar wind carries a message across the void, etching its signature into the rings in ways we're only beginning to decode. And as we study these distant interactions, we're reminded that the solar system is a web of connections where even the quietest whisper from the Sun can shout across the darkness, leaving its mark on the grandest of cosmic canvases. NASA Cassini spacecraft didn't just study Saturn's rings, it rewrote the textbook on them. For 13 years, this robotic explorer orbited the gas giant, capturing details so precise they revealed structures no one knew existed. Before Cassini, planetary rings were often dismissed as simple disks of debris, but its cameras and instruments uncovered a world of chaos and elegance, where storms the size of continents raged silently and gravity painted spirals finer than any artist's brushstroke. One of its most startling discoveries was the sheer dynamism of the rings. Time-lapse images showed propeller features moving, gaps shifting, and waves propagating like ripples in a pond, proof that these weren't static relics but living, breathing systems. The spacecraft's toolkit was as impressive as its findings. Its radar pierced through thick ring layers, mapping densities and compositions hidden from optical cameras. The cosmic dust analyzer caught microscopic particles one by one, revealing their chemical fingerprints. But perhaps its most dramatic contribution was the grand finale, a series of daring dives between Saturn and its innermost rings in 2017. Flying closer than any probe before it, Cassini measured the ring's mass with unprecedented precision, solving a centuries-old mystery. Turns out, Saturn's rings are far lighter than expected, suggesting they might be relatively young, perhaps forming only 100 million years ago, a blink in cosmic time. Some of Cassini's revelations bordered on poetic. It spotted vertical structures in the rings towering 2 miles high, casting long shadows during Saturn's equinox. These peaks were caused by tiny moonlets embedded within the rings, their gravity pulling particles upward like threads in a tapestry. Then there were the straws, clumps of ring material so tightly packed they resembled strands of hay, fleeting yet dense enough to momentarily baffle scientists. Even the gaps surprised researchers. The Keeler Gap, once assumed to be near empty, was found to host a population of icy snowballs, each a few feet across, dancing around Daphnes like moths around a flame. Cassini's legacy isn't just about the data it collected, but the questions it ignited. Why do some spiral waves in the rings dampen out quickly while others persist for centuries? How do moonlets the size of a house survive in the rings without being shattered by collisions? These puzzles keep scientists busy years after the mission's fiery conclusion, as they comb through terabytes of archived data, uncovering nuances missed during the initial frenzy of discovery. The mission also transformed how we study planetary rings across the solar system. Techniques perfected by Cassini, like using stellar occultations to measure ring transparency, are now applied to Jupiter's faint arcs and Uranus's dark bands. Its discoveries even influenced the search for rings around exoplanets, proving that these structures aren't mere curiosities but vital laboratories for understanding cosmic physics. Every image, every dataset was a reminder that nature's creativity far outstrips our imagination. From the delicate filigree of electrostatic spokes to the brute force of gravitational resonances, Cassini showed us that rings aren't just features, they're stories written in ice and dust waiting to be read. Cosmic storms may unfold over millions of miles, but scientists have found a way to shrink them down to desktop scale, not with magic, but with cutting-edge simulations that bring the chaos of planetary rings into the lab. Picture a high-powered computer humming away, its algorithms calculating the precise dance of countless particles, each one representing a fragment of ice or dust in Saturn's rings. These virtual arenas aren't just simplified models, they're staggeringly complex reconstructions, factoring in everything from gravitational tugs to electromagnetic nudges, even the way particles stick together or shatter on impact. One simulation might focus on how a moon's gravity sends ripples spiraling through the rings, while another tests how solar wind charges dust grains, sparking miniature storms. The goal isn't just to mimic what we see through telescopes, it's to uncover the hidden rules governing these celestial tempests. Some experiments take a more hands-on approach. In labs, researchers use vacuum chambers to mimic the near-weightless environment of space, filling them with fine powders or tiny beads to stand in for ring particles. Then they introduce forces like electrostatic charges or magnetic fields, watching as the debris organizes itself into familiar patterns, spiral waves, clumps, even propeller-like disturbances. It's like watching a cosmic storm in fast forward, with results that often mirror Cassini's snapshots of Saturn's rings. These tabletop tornadoes reveal something profound. The same physics that sculpts planetary rings can be recreated with nothing more than everyday materials and ingenuity. But simulations have their limits. Even the most powerful computers can't perfectly account for every variable in a system as vast and messy as a planetary ring. Tiny discrepancies, a missed collision, an underestimated charge can snowball into wildly different outcomes. That's why scientists use a one-two punch, simulations to generate hypotheses and spacecraft data to test them. When Cassini spotted a peculiar ripple in Saturn's D-ring, for instance, modelers raced to retrace its steps, tweaking their virtual rings until they matched the observation. Sometimes the solution lies in factors no one initially considered, like the way sunlight warms one side of a particle more than the other, subtly altering its path. What makes these experiments so revolutionary is their predictive power. By simulating storms under different conditions varying a moon's orbit, amplifying magnetic fields, researchers can forecast how real rings might behave decades or even centuries from now. Some models suggest Saturn's iconic spokes could vanish during periods of low solar activity, while others hint at undiscovered moonlets lurking in Uranus's dark rings, waiting to be confirmed by future telescopes. These digital crystal balls don't just satisfy curiosity, they guide missions, helping engineers time observations or steer spacecraft toward the most promising surprises. Yet for all their sophistication, lab storms will never replace the real thing. There's an irreplaceable magic in seeing Saturn's rings through a spacecraft's lens, knowing each ripple and gap was sculpted by forces we're only beginning to grasp. Simulations bridge the gap between theory and reality, offering a sandbox where scientists can play with the universe's variables and sometimes stumble onto truths no telescope could have revealed alone. As these virtual rings grow ever more detailed, they remind us that the cosmos isn't just out there. It's also in the hum of a supercomputer, the swirl of dust in a vacuum chamber, and the endless curiosity that drives us to bring the heavens down to Earth. For centuries, Saturn's rings stood alone as the definitive example of what planetary rings could be, until astronomers began peering beyond our solar system and asking a tantalizing question: what if rings aren't unique to Saturn? The hunt for exoplanetary rings, or exorings, has become one of modern astronomy's most thrilling challenges. Imagine a world 10 times Jupiter's size, its rings so vast they dwarf Saturn's, casting shadows light-years long, or a rocky super-Earth circled by thin, shimmering hoops of volcanic dust. These aren't just hypotheticals, they're possibilities waiting to be confirmed, hidden in the glare of distant stars. Detecting exorings is like trying to spot a pinprick of light next to a floodlight. Most exoplanets are found via the transit method, measuring the dip in a star's brightness as a planet crosses in front of it. Rings complicate this. Instead of a clean, symmetrical dimming, they could produce subtle asymmetries or extended dips as the rings block starlight before and after the planet itself transits. Some researchers even look for telltale scattering effects, where ring particles bend light in unique ways, creating a faint glow visible in infrared. The challenge is separating these signals from other phenomena, like passing clouds of interstellar dust or the planet's own atmosphere, yet the potential rewards are staggering. Exorings could reveal entirely new classes of ring system structures sculpted by environments unlike anything in our solar system. Picture a planet orbiting a pulsar, its rings pulsing with radiation, or a gas giant so close to its star that solar winds blast its rings into bizarre, elongated shapes. Some theories suggest mega-rings might form around young, massive planets, where the sheer gravitational pull could capture and shape debris on scales we've never witnessed. Each discovery wouldn't just add to a catalog, it would rewrite the rules of how rings form and evolve under extreme conditions. The search has already yielded intriguing candidates. In 2012, observations of the young star J1407 hinted at a possible ring system around its companion object, a planet or brown dwarf, with rings 200 times wider than Saturn's. Dubbed Super Saturn, this unconfirmed giant remains a mystery, but it's a beacon for what might be out there. More recently, the exoplanet HOP 41378F showed anomalous transit data that some scientists argue could point to rings, though others attribute it to a tilted orbit. These ambiguous cases are the frontier, where every new telescope brings us closer to answers. What makes exorings so scientifically valuable isn't just their novelty, it's their ability to serve as cosmic laboratories. Around a distant star, rings might form from shattered moons, interstellar debris, or even remnants of planetary collisions, each scenario leaving distinct chemical or structural fingerprints. By comparing them to Saturn's rings, astronomers could test universal theories about how gravity, magnetism, and particle dynamics interact across the galaxy. And if we find rings around an Earth-sized exoplanet, that could revolutionize our understanding of habitability, suggesting that even rocky worlds might host stable, complex ring systems. The hunt is accelerating. Upcoming telescopes like the James Webb Space Telescope and the Extremely Large Telescope will peer deeper into exoplanetary transits, hunting for the faint signatures of rings. Future missions might even directly image exorings around nearby stars, capturing their delicate structures in unprecedented detail. Every improvement in sensitivity brings us closer to spotting the first definitive exoring, and with it, a new chapter in our understanding of cosmic artistry. Beyond the science, there's something profoundly humbling about this search. If rings exist around other worlds, they're a reminder that the universe loves repetition, not just in stars and planets, but in the delicate adornments that grace them. Whether it's Saturn's icy bands or a hypothetical mega ring glowing in the depths of space, these structures whisper the same truth. Chaos and beauty are universal languages, spoken across the cosmos in rings, waves, and storms we're only beginning to decode. The next decade of space exploration is poised to revolutionize our understanding of cosmic storms, with missions designed to peel back the layers of these invisible phenomena like never before. NASA Dragonfly, a rotorcraft destined for Saturn's moon Titan, might seem an unlikely candidate to study ring storms until you consider its suite of instruments capable of analyzing atmospheric chemistry and charged particle interactions. While Titan itself lacks rings, its hazy atmosphere and complex organic chemistry mirror processes that could occur in ring systems, offering clues about how storms shape particulate matter across the solar system. Meanwhile, the European Space Agency's JUICE mission will zero in on Jupiter's faint rings, deploying ice-penetrating radar and particle detectors to map disturbances invisible to optical telescopes. These tools will catch the whispers of electromagnetic turbulence and gravitational ripples, revealing how Jupiter's colossal magnetosphere stirs its rings into fleeting tempests. What sets these missions apart isn't just their technology, it's their strategy. Unlike Cassini, which observed Saturn's rings from a distance, future missions will exploit orbital dynamics to study storms in real time. Imagine JUICE threading the needle between Jupiter and its gossamer rings, measuring how solar wind and magnetic fields sculpt dust particles minute by minute. Or Dragonfly's sensors detecting methane storms on Titan that could mimic the electrostatic forces at work in Saturn's B ring. These missions won't just capture snapshots, they'll record the ring's pulse, tracking how storms evolve across days, seasons, even decades. The stakes are high. Data from these missions could settle long-standing debates like whether Saturn's rings are truly young, or if their apparent lightness is a red herring caused by hidden denser material. They might also uncover entirely new classes of storms. Jupiter's diffuse rings, for instance, could harbor dust tsunamis, where waves of charged particles surge outward after moonlet collisions, a phenomenon never before observed. And let's not forget Uranus and Neptune, often overlooked in favor of their flashier cousins, but whose tilted magnetic fields and erratic ring arcs could hide storms unlike anything in our models. Beyond hardware, these missions embody a shift in how we explore. Collaborative networks will pool data from orbiters, landers, and Earth-based telescopes, creating a multidimensional portrait of ring storms. Citizen scientists might even play a role, sifting through mission data to spot anomalies algorithms miss. It's a reminder that decoding these cosmic sculptures isn't just a job for robots, it's a human endeavor, fueled by curiosity and the thrill of the unknown. The true promise of these missions lies in their surprises. Cassini taught us that every new vantage point reveals something unexpected, whether it's the towering vertical structures in Saturn's rings or the ethereal spokes that materialize like clockwork. As Dragonfly and JUICE peel back the veil on ring storms, they won't just answer old questions, they'll ask new ones, proving once again that the universe's artistry is boundless, and its secrets are waiting for those bold enough to look closer. There's a mesmerizing symmetry between the spirals carved by cosmic storms in Saturn's rings and the brushstrokes of a master painter, both born from chaos, both guided by invisible hands. The universe doesn't just obey the laws of physics, it elevates them to art. Take the spiral density waves, for example. These vast, coiled formations, etched by the gravity of passing moons, mirror the logarithmic spirals found in seashells and galaxies. It's as if nature has a favorite blueprint, one it revisits, whether crafting something as intimate as a nautilus or as grand as a ring system stretching 70,000 miles across. Even the jagged edges of Uranus's rings, tilted and uneven, recall the fractured beauty of abstract expressionism, proof that disorder can be just as deliberate as precision. The resemblance isn't accidental. The same mathematical principles that govern fluid dynamics, the way water swirls in a drain or smoke curls in the air, also shape the storms in planetary rings. When Cassini captured the spokes in Saturn's B ring, transient shadows flickering like piano keys, it wasn't just documenting physics, it was capturing a performance. These spokes, caused by dust particles levitating above the ring plane, arrange themselves in patterns reminiscent of minimalist art, where simplicity reveals depth. The universe, it seems, has an eye for composition. Human artists have long drawn inspiration from nature's rhythms. Think of Van Gogh's starry skies or Hokusai's waves, but cosmic storms flip the script. Here, nature isn't the muse, it's the artist sculpting with forces we can barely measure. The Keeler Gap's scalloped edges, carved by the tiny moon Daphnes, could pass for the delicate grooves of a woodcut, while the propeller features, those fleeting wing-shaped disturbances, evoke the kinetic energy of a colder mobile. Even the colors tell a story. Saturn's icy rings glow pale gold in sunlight, their hue shifting with the angle of illumination, much like the play of light on a Renaissance canvas. This interplay between art and science isn't just poetic, it's practical. Scientists often turn to artistic techniques to visualize data, transforming radio waves into false color images that reveal hidden storms. Conversely, artists collaborate with astrophysicists to create installations that translate cosmic phenomena into immersive experiences. A ripple in the rings becomes a sound wave. A moon's gravitational nudge becomes a dancer's pivot. The boundaries blur, reminding us that curiosity and creativity are two sides of the same coin. What makes these celestial artworks so profound is their impermanence. A spiral wave might last centuries, a spoke mere hours, yet each is a testament to the universe's restless ingenuity. They challenge us to see beauty not just in stillness but in flux, in the way a storm can be both destructive and generative, erasing one pattern while scribing another. And perhaps that's the greatest lesson of all. The cosmos doesn't just create, it composes. Every collision, every surge of magnetism is a note in a symphony we're only beginning to hear. The study of cosmic storms isn't just for professional astronomers in white coats. Some of the most exciting discoveries have come from everyday people with a passion for the cosmos. Imagine scrolling through images of Saturn's rings on your laptop, sipping coffee, when suddenly you spot something odd, a faint ripple, an unexplained streak, a pattern no algorithm has flagged. This isn't science fiction. It's the reality for thousands of citizen scientists who have joined projects like Planet Hunters and Zooniverse, turning their curiosity into genuine contributions to space exploration. These volunteers have combed through mountains of data from missions like Cassini, identifying anomalies that even sophisticated software might miss. In one striking case, an amateur astronomer noticed a peculiar kink in Saturn's F-ring, a disturbance later confirmed to be the gravitational footprint of a tiny, previously unknown moonlet. What makes this collaborative approach so powerful is its accessibility. You don't need a PhD to recognize unusual features in ring structures. You just need curiosity and a sharp eye. Platforms like NASA Solar System Treks allow anyone to explore high-resolution images of planetary rings, tagging potential storms or oddities for researchers to investigate. This crowdsourced model doesn't just accelerate discovery, it reshapes who gets to participate in science. A teacher in Brazil, a retiree in Norway, or a high school student in India can all play a role in unraveling the mysteries of cosmic storms, blurring the lines between professional and amateur in the best possible way. The impact goes beyond spotting anomalies. Enthusiasts worldwide contribute to tracking long-term changes in ring systems, noting how storms evolve or how spokes fade and reappear with Saturn's seasons. Online forums buzz with discussions about propeller features or the odd behavior of Uranus's ragged rings, creating a global brain trust of collective observation. Some citizen scientists have even co-authored papers, their names listed alongside career researchers, a testament to how democratized space science has become. Projects like these also bridge gaps in public understanding. When people engage directly with real data, misconceptions about planetary rings, like the myth that they're solid or permanent, melt away. Instead, participants see rings for what they truly are: dynamic, ever-changing systems where storms sculpt and resculpt the landscape. This hands-on involvement fosters a deeper appreciation for the scientific process, revealing how discovery isn't just about eureka moments but meticulous observation and collaboration. The beauty of public engagement lies in its ripple effect. Every new volunteer brings fresh perspectives, whether it's an artist noticing aesthetic patterns in spiral waves or a programmer developing tools to visualize ring-particle collisions. Schools and museums have embraced these initiatives too, using planetary ring data as teaching tools to spark interest in physics and astronomy. The result: a growing community that doesn't just consume science but actively shapes it, proving that the universe's wonders aren't reserved for a select few. They're there for anyone willing to look. And the best part, this is just the beginning. As AI and machine learning advance, citizen scientists are partnering with algorithms, training them to recognize subtle storm signatures in vast datasets. Future missions might rely on this hybrid approach, where human intuition and artificial intelligence work in tandem to decode the cosmos. So the next time you gaze at an image of Saturn's rings, remember, you might be one click away from uncovering something no one else has seen. After all, the universe doesn't discriminate, it hides its secrets in plain sight, waiting for the right pair of eyes to notice. Hollywood loves to depict planetary rings as solid, gleaming hoops like a giant hula hoop wrapped around a planet. But the truth is far more fascinating. Those pristine bands we see in movies would shatter instantly in reality, because planetary rings are anything but rigid. They're more like a bustling highway during rush hour, with countless particles, some as fine as dust, others as large as houses, zipping past each other at thousands of miles per hour, constantly colliding, bouncing, and reshaping the entire structure. Imagine trying to walk across a river of ice boulders, each one moving at different speeds, and you'll start to grasp the chaotic beauty of these cosmic disks. Another myth: that rings are timeless ornaments, unchanging over millennia. In truth, they're more like ephemeral sand sculptures on a cosmic beach, constantly reshaped by invisible hands. Saturn's iconic rings, for instance, might be less than 100 million years old, a blink in cosmic terms, and they're already fading. Ring rain, the slow but steady shower of particles into Saturn's atmosphere, is draining them away, while cosmic storms churn the remaining material into new formations. Some structures, like the propeller features carved by hidden moonlets, vanish within weeks, while spiral density waves can persist for centuries before dissipating. This isn't a frozen snapshot, it's a live performance with gravity, magnetism, and chaos as the lead actors. Even the idea that rings are flat, two-dimensional belts is misleading. High-resolution images from Cassini revealed vertical structures towering miles above the ring plane, cast in stark relief during Saturn's equinox. Tiny moonlets within the rings tug particles upward, creating peaks and troughs that defy the classic vinyl record analogy. And let's not forget the spokes, those ghostly radial streaks that appear and vanish like clockwork, levitating dust particles suspended by electromagnetic forces. Rings aren't just dynamic, they're multidimensional, with layers of activity unfolding above and below their central plane. Perhaps the most persistent misconception is that all rings are created equal. Saturn's dazzling ice-dominated system steals the spotlight, but Jupiter's wispy dust rings and Uranus's jagged, charcoal dark bands operate by entirely different rules. Neptune's fragmented arcs, held together by the delicate nudges of shepherd moons, barely resemble rings at all. Each system is a unique laboratory, revealing how gravity, chemistry, and even solar wind conspire to create structures that defy one-size-fits-all explanations. Dispelling these myths isn't just about accuracy, it's about unlocking wonder. When we stop seeing rings as static postcards and start appreciating them as living, evolving systems, every storm, every ripple becomes a clue to the universe's grand mechanics. The next time you gaze at Saturn through a telescope, remember, you're not looking at a frozen jewel. You're witnessing a cosmic construction zone where the forces of nature are always at work, sculpting the invisible and ephemeral into something briefly, breathtakingly tangible. Planetary rings might seem like local oddities, but they're part of a grander cosmic family: astrophysical disks, those vast, spinning platters of gas and dust that serve as cradles for worlds. Beyond Saturn's icy halos, similar disks stretch across the universe, from the dense, star-forming nebulae of Orion to the fledgling systems around newborn stars light years away. What makes these connections so electrifying isn't just their shared shape, it's the way the same invisible forces sculpt them all. Gravity, turbulence, and electromagnetic whispers don't just shape Saturn's rings, they're the very tools that carve planets from the chaos of protoplanetary disks. Take a young star like HL Tauri, its swirling disk captured in stunning detail by the Atacama Large Millimeter Array. The dark gaps in its dust resemble Saturn's divisions, but on a scale hundreds of times larger. Scientists now suspect those gaps aren't empty. They're likely carved by infant planets, their gravity clearing paths just as Daphne's sculpts the Keeler Gap. The spirals winding through these distant disks, they're cosmic twins to Saturn's density waves, born from the same gravitational nudges that orchestrate ring particles. Even the tempests within protoplanetary disks, violent vortices where particles clump and collide, mirror the storms churning through planetary rings, just with higher stakes. Instead of transient ripples, these disturbances might seed the birth of entire worlds. The parallels run deeper than mere appearance. In both systems, tiny particles face a universe of forces trying to pull them apart. In Saturn's rings, electrostatic charges can levitate dust, creating spokes. In protoplanetary disks, magnetic fields twist and contort, funneling material into planet-forming eddies. Even the delicate dance of shepherd moons finds its counterpart in disk shepherds, planets in the making whose gravity herds dust into narrow bands, priming it for collapse into moons or larger bodies. The same physics scales effortlessly from the intimate to the epic, proving that a ripple in Saturn's rings and a planet's birth cry are verses in the same cosmic poem. Studying ring storms offers a unique advantage: proximity. While protoplanetary disks are light years away, Saturn's rings are in our celestial backyard, letting scientists test theories in real time. When Cassini observed how moonlets stir propeller features, it provided a blueprint for how baby planets might grow in distant disks, starting as pebbles, then snowballing through collisions until gravity takes over. The chaotic migration of moonlets like Pan, hopping between ring layers, might even explain why some exoplanets orbit bizarrely close to their stars, as if they'd spiraled inward long ago. Yet differences remain, and they're just as enlightening. Protoplanetary disks are far more massive, their particles swaddled in gas that dampens storms and alters dynamics. Rings, by contrast, are gas-poor, making their disturbances sharper, their storms more abrupt. Comparing the two is like studying fire in oxygen versus a vacuum. The same laws apply, but the outcomes diverge spectacularly. These contrasts help scientists isolate variables, teasing out which phenomena are universal and which depend on environment. The ultimate prize, understanding how randomness becomes order. Whether it's ring particles aligning into spiral waves or dust grains in a protostellar disk clumping into planetesimals, the universe has a knack for sculpting chaos into structure. By decoding the storms in Saturn's rings, we're glimpsing the same processes that, on a larger canvas, might have birthed Earth itself. Every gap, every ripple, is a clue to the universe's quiet obsession turning debris into destiny, one particle at a time. Space exploration isn't just about discovery, it's also about stewardship. As we send probes and spacecraft to study planetary rings, we're faced with a delicate balancing act: how to unravel their mysteries without leaving our own mark on these pristine environments. Consider the icy particles of Saturn's rings, untouched by human hands for billions of years. A single microbe hitchhiking on a spacecraft could contaminate this ancient material, skewing data about the ring's composition, or even giving false clues about the potential for extraterrestrial life. It's not science fiction. It's a real concern that agencies like NASA and ESA take seriously, enforcing strict protocols to sterilize spacecraft and minimize biological contamination. But the ethical questions run deeper than microbes. Planetary rings are more than scientific curiosities, they're natural archives, preserving clues about the early solar system in their icy layers. Disturbing them carelessly could erase information we didn't even know we needed. Imagine a scenario where a future mission, in its eagerness to sample ring material, inadvertently triggers a chain reaction of collisions, altering the very structures we aim to study. The ring's fragility makes them uniquely vulnerable. A nudge in the wrong place could send ripples through the system that last for centuries. This isn't hypothetical. Cassini's grand finale plunge into Saturn was carefully planned to avoid contaminating moons like Enceladus, which might harbor life-friendly conditions beneath its icy crust. The ethical framework extends to how we share these discoveries. Data from ring studies shouldn't be hoarded by a handful of space agencies, but made accessible to scientists worldwide, including researchers from nations without their own space programs. When the James Webb Space Telescope peers at distant exorings, or when JUICE analyzes Jupiter's faint rings, the findings belong to humanity as a whole. This inclusivity isn't just altruistic, it's practical. Diverse perspectives lead to breakthroughs, whether it's a team in India spotting a new ring storm pattern or a student in Chile reanalyzing decades-old data to uncover hidden trends. Then there's the question of preservation versus progress. Some argue that stringent planetary protection measures slow innovation, adding costs and delays to missions. Others counter that without these safeguards, we risk becoming interplanetary vandals, prioritizing short-term gains over long-term understanding. The compromise lies in smarter exploration, designing missions that observe without interfering, like using lasers to analyze ring composition from a distance instead of physically collecting samples. Technology is catching up to ethics, with advancements in spectroscopy and remote sensing reducing the need for invasive contact. the stakes feel even higher when we consider future generations. The rings we see today might not last forever. Saturns are already fading due to ring rain. Our responsibility isn't just to study them, but to ensure they remain as undisturbed as possible for the scientists of tomorrow, who may have tools and questions we can't yet imagine. It's the same principle behind leaving wilderness untouched, not because we can't explore it, but because some things hold value in their natural state. Planetary rings are more than research subjects. They're cosmic wonders that inspire awe and curiosity across cultures and ages. Ultimately, ethical space exploration recognizes that we're not just visitors to these distant realms, we're caretakers. Every mission to Saturn or Jupiter carries an unspoken promise: to tread lightly, to observe humbly, and to leave the universe's artistry as we found it, so that its beauty and secrets remain intact for all who follow. The rings have survived eons without us. Our challenge is to ensure they endure, pristine and mysterious, long after our probes have fallen silent. Cosmic storms aren't just reshaping planetary rings, they're reshaping futures. Picture a classroom where students huddle around a screen, watching Cassini's footage of Saturn's spiraling density waves. The moment those ghostly patterns flicker to life, something sparks. A hand shoots up. How does gravity do that? Suddenly, abstract equations in a textbook transform into a cosmic mystery begging to be solved. This is the power of planetary rings as teaching tools. They don't just explain science, they ignite it. Educators tapping into these phenomena find eager audiences because rings are more than lessons. They're gateways. A child who learns how tiny moonlets carve propeller features might glimpse their own potential to uncover hidden truths, whether in space or a lab. The secret lies in their tangibility. Unlike black holes or dark matter, planetary rings live in the Goldilocks zone of cosmic education, complex enough to challenge young minds, yet visible enough to feel real. Take shepherd moons. The idea that a moon no bigger than a city can sculpt gaps thousands of miles wide is both counterintuitive and exhilarating. Demonstrating this with a simple experiment: swirling glitter in a dish and nudging it with a magnet makes celestial mechanics tactile. Suddenly, gravity isn't just a force, it's a sculptor's hand, and every student holding that dish is holding a piece of the universe. Programs like NASA STEM workshops leverage this wonder, tasking kids with designing their own ring systems using coding or physics simulations. One standout project had teens recreate Saturn's spoke features with electrostatic sand in microgravity chambers, revealing how charged particles dance to invisible tunes. These aren't just activities, they're revelations. When a 14-year-old tweaks a variable and watches her digital rings erupt in storms, she's not just learning, she's commanding the cosmos. The ripple effect extends beyond classrooms. Amateur astronomy clubs report surges in membership after public observations of Saturn's rings, where newcomers peer through telescopes and gasp at structures they've only seen in photos. Social media amplifies this, with viral TikTok breakdowns of ring science racking up millions of views. One viral thread debunking why Saturn's rings are disappearing became a rallying cry for young environmentalists, drawing parallels to Earth's fragile systems. Rings, it turns out, teach planetary stewardship as deftly as physics. But the real magic happens when curiosity outpaces curriculum. Consider the student who, after a planetarium show on cosmic storms, scours library archives for Voyager data to track changes in Uranus's rings over decades. Or the high school team that built a low-cost radio telescope to detect Jupiter's ring particles and wound up discovering an anomaly professionals had missed. These stories aren't outliers, they're proof that when we frame science as exploration rather than memorization, kids don't just consume knowledge, they chase it. The legacy of these efforts isn't just future scientists, it's future artists sketching ring systems for sci-fi novels, engineers inspired by Cassini's precision, and teachers who'll pass the torch anew. Because the greatest lesson planetary rings teach isn't about gravity or storms, it's that the universe is a puzzle waiting for fresh eyes to solve it. And sometimes all it takes is one glimpse of Saturn's spirals to set those eyes alight. Cosmic storms in planetary rings are more than just celestial phenomena. They're cosmic riddles that blur the line between chaos and harmony. Consider the paradox they present. These tempests arise from randomness, colliding particles, fluctuating magnetic fields, the gravitational tug of passing moons, yet they sculpt formations of astonishing precision. Spiral density waves unwind with mathematical perfection, their curves echoing the golden ratio found in sunflowers and seashells. The Keeler gap's edges stay sharp despite the constant bombardment of debris, as if an invisible hand maintains their crisp boundaries against entropy's relentless pull. How does disorder birth such order? The rings offer no easy answers, only deeper questions about whether the universe favors chaos or if chaos itself is a kind of order we're still learning to decipher. These transient sculptures also challenge our perception of time. A single storm might rage for centuries, its waves propagating slower than a growing tree, yet vanish in the blink of a geological eye. The propeller features carved by moonlets last mere weeks, cosmic mayflies in a system billions of years old. This interplay of scales forces us to confront uncomfortable truths, that human lifetimes are insignificant against celestial clocks, yet our curiosity lets us witness processes no other species could comprehend. The rings become a mirror, reflecting our own fleeting existence against the vastness of deep time. Then there's the question of agency. We often describe cosmic storms as if they're actors: gravity, carves, magnetism, sculpts, moons, shepherd. But these are metaphors, human attempts to impose narrative on impersonal forces. The reality is both humbler and more profound. The universe creates beauty without intent, artistry without an artist. A spiral wave in Saturn's rings isn't designed, it emerges from countless mindless collisions, each obeying simple physical laws. This revelation reshapes how we see creativity itself. If splendor can arise from chaos, what does that say about the origins of life or the structure of consciousness? Perhaps the most unsettling implication is how much remains unseen. For every spoke, feature, or gap we've catalogued, there are surely storms and structures lurking beyond our detection, disturbances in frequencies we can't measure, patterns too vast or too subtle for our instruments. The rings remind us that reality isn't limited to what we perceive. Invisible forces are perpetually at work, crafting marvels we may never witness. This isn't discouragement, it's an invitation. The universe isn't a puzzle to be solved, but a mystery to be explored, and every answered question unveils new enigmas. Ultimately, planetary rings are more than icy debris, they're philosophical laboratories. Their storms whisper that chaos and order aren't opposites but partners in an eternal dance, that time is both fluid and fragmented, and that the cosmos teems with creativity even in its emptiness. To study them isn't just to map Saturn's backyard, it's to sketch the boundaries of human understanding and to glimpse, however faintly, the principles that might shape everything from atoms to galaxies. The true gift of these cosmic storms isn't the answers they provide, but the awe they inspire, the reminder that wonder is the compass pointing us toward the next great unknown. The tools we use to study cosmic storms in planetary rings have undergone a revolution so profound, it's as if we've traded candlelight for lasers. Gone are the days when astronomers squinted through telescopes, piecing together blurry snapshots of Saturn's rings. Today's observatories wield adaptive optics that bend starlight itself, counteracting the distorting ripple of Earth's atmosphere in real time. Imagine a mirror that flexes 1,000 times per second. That's the magic behind instruments like the Keck Observatory, which now spots ring storms with clarity rivaling spacecraft images. But the breakthroughs don't stop at sharper visuals. Spectrometers aboard probes like Cassini dissected sunlight filtering through the rings, revealing chemical fingerprints of particles too small to see directly, grains of iron, silicates, and even organic compounds we once assumed were absent from these icy realms. Artificial intelligence has become the silent partner in this cosmic detective work. Machine learning algorithms sift through decades of ring data, spotting patterns no human eye could catch, like the faint gravitational signature of a hidden moonlet or the subtle brightening of a spiral wave before it fully forms. At NASA Jet Propulsion Laboratory, neural networks trained on Cassini's archive now predict storm activity in Saturn's rings with eerie accuracy, turning raw data into forecasting tools. These AI models don't just analyze, they hypothesize, suggesting where to aim telescopes next or flagging anomalies that defy existing theories. One algorithm recently identified a strange kink in Uranus's Epsilon ring, a feature later confirmed to align with the planet's lopsided magnetic field, a connection humans had overlooked for decades. The next generation of space telescopes promises even wilder leaps. The James Webb Space Telescope's infrared eyes can peer through the haze of distant ring systems, measuring their heat signatures to infer particle sizes and storm frequencies. Meanwhile, the upcoming Nancy Grace Roman Space Telescope will map exoplanetary rings by the shadows they cast during transits, hunting for the telltale flickers of cosmic storms in alien star systems. Back on Earth, radio telescope arrays like ALMA stitch together signals from dozens of antennas, creating virtual telescopes the size of continents capable of resolving details as fine as a freight train on the moon. These instruments don't just show us rings, they let us eavesdrop on their dynamics, catching the whispers of collisions and the hum of electromagnetic turbulence. Perhaps the most transformative advances lie in miniaturization. CubeSats satellites no bigger than a toaster now carry spectrometers and particle detectors into deep space at a fraction of traditional mission costs. Swarms of these tiny probes could soon orbit Saturn simultaneously, creating a 3D weather map of ring storms as they evolve. Even amateur astronomers contribute, with backyard telescopes equipped with high-speed cameras capturing transient events, like the 2021 outburst in Saturn's F-ring, later confirmed by professional observatories to be a moonlet collision. This democratization of tools means the next big discovery might come from a university lab, a high school club, or a lone enthusiast staring at the night sky. The true power of these technologies isn't just in what they reveal, but how they reshape our questions. Adaptive optics exposed vertical structures in Saturn's rings that defy flat disk models. AI-driven simulations suggested that some propeller features might be temporary traps for ring material, not just scars from passing moonlets. Every upgrade in resolution or sensitivity doesn't just add detail, it rewrites the narrative. As we stand on the brink of this observational renaissance, one thing is certain: the rings have been keeping secrets, and the tools to uncover them are finally catching up. Unlocking the secrets of cosmic storms isn't a solo mission, it's a symphony of expertise, where astronomers, physicists, and engineers each bring their unique instruments to the orchestra. Picture an astronomer peering through a telescope, spotting a strange ripple in Saturn's rings. That observation sparks a physicist's curiosity. What forces could bend a ring's structure so precisely? Meanwhile, an engineer tweaks a spacecraft's antenna to capture radio waves from those ripples, translating their faint whispers into data. This isn't just teamwork, it's intellectual alchemy, where disparate disciplines combine to reveal what no single field could uncover alone. Take the mystery of Saturn's spoke features, those ghostly radial streaks that appear and vanish like clockwork. Astronomers first documented them in Voyager images, but it took plasma physicists to recognize their connection to Saturn's magnetic field. Then came the engineers, designing Cassini's instruments to measure the electric charge of ring particles, confirming the spokes were born from dust levitating above the ring plane. Without this triad of perspectives, the spokes might have remained a celestial footnote instead of a window into electromagnetism's role in shaping rings. The magic lies in the friction between disciplines. A physicist might model a ring storm using equations, while an astronomer insists the model must account for real-world imperfections like the way a passing moon's gravity scatters particles unpredictably. Engineers bridge the gap, building sensors sensitive enough to detect those chaotic nuances. It's in these collisions of worldview that breakthroughs ignite. When Cassini's cameras caught propeller features moving through Saturn's rings, it wasn't just a discovery about orbital mechanics, it was a triumph of collaboration. Dynamicists calculated the moonlet's masses, materials scientists analyzed the propeller shapes for clues about particle composition, and mission planners adjusted the spacecraft's orbit to capture follow-up images. This interdisciplinary dance extends far beyond space missions. Laboratories on Earth recreate ring conditions using plasma chambers and laser-scattered microspheres, offering controlled environments to test theories. Computer scientists write algorithms to simulate millions of particle collisions, revealing patterns invisible to the naked eye. Even artists contribute, visualizing data in ways that reveal hidden symmetries or anomalies. The most profound discoveries often emerge at these intersections, like the realization that spiral density waves in rings behave similarly to traffic jams on highways, an insight borrowed from fluid dynamics. The urgency of collaboration grows as questions deepen. To understand why some ring storms erupt suddenly while others simmer for centuries, we need astrophysicists to model magnetic fields, chemists to study ice particle adhesion, and statisticians to parse decades of observational data. No single lens is sufficient. When the JUICE mission probes Jupiter's rings in the 2030s, its findings will hinge on this cross-pollination, how magnetospheric experts interpret charged particle flows alongside geologists deciphering dust composition. What makes this approach so powerful isn't just the sum of its parts, but the surprises it uncovers. A radar engineer tweaking an antenna might stumble on a new resonance frequency that reveals hidden moonlets. A materials physicist studying ice friction could accidentally explain why certain ring regions resist storm formation. These aren't hypotheticals, they're the history of ring science, written in collaborative breakthroughs. And the ripple effect extends beyond academia. Teachers blend these interdisciplinary lessons into classrooms, showing students how physics equations describe real cosmic phenomena. Amateur astronomers partner with professionals to monitor ring changes, their observations refining models. The lines between expert and enthusiast blur, proving that the universe's greatest puzzles aren't solved in isolation, but through the collective curiosity of minds wired differently. The lesson is clear: cosmic storms don't respect disciplinary boundaries, so neither can we. Whether it's a theorist's hunch, an observer's sharp eye, or an engineer's clever workaround, each perspective is a piece of the puzzle. And as these pieces snap together, they don't just solve mysteries, they reveal new ones, ensuring the dance of discovery never ends. When you think of cutting-edge planetary science, you might picture billion-dollar space telescopes or teams of PhDs analyzing supercomputer simulations. But some of the most exciting discoveries about cosmic storms in planetary rings come from backyard astronomers with nothing more than a passion for the night sky and a decent telescope. These amateur observers have become the unsung heroes of ring science, spotting subtle shifts in Saturn's brightness or catching transient storms that professional observatories might miss. Take the case of the 2021 F-ring outburst, a sudden flare in Saturn's outermost ring first noticed by an amateur in Japan using an 8-inch telescope. His alert sent professional astronomers scrambling to train the Keck Observatory on the event, revealing a violent collision between a rogue asteroid and the ring itself. Without that initial tip, the encounter might have gone unrecorded, just another whisper in the ring's endless turbulence. What makes amateur contributions so invaluable isn't just their eyes, it's their persistence. While professional telescopes operate on tight schedules, backyard astronomers can monitor planetary rings night after night, tracking long-term changes that fall through the cracks of big-budget projects. Some have spent decades logging fluctuations in Saturn's ring brightness, creating datasets that reveal seasonal patterns no single mission could capture. Others specialize in catching spoke formations, those elusive, radial ghosts in Saturn's B ring, documenting their appearances and disappearances with a dedication that rivals any lab. Their work isn't just supplemental, it's foundational, filling gaps in our understanding of how ring storms evolve over human timescales rather than celestial ones. Technology has democratized this collaboration even further. Free software like WinJupos lets amateurs process planetary images with professional-grade precision, measuring ring features down to arcseconds. Online platforms like the Planetary Virtual Observatory and Laboratory aggregate these observations, turning thousands of individual snapshots into a living atlas of ring activity. During the 2017 grand finale of NASA Cassini mission, amateurs worldwide coordinated observations to complement the spacecraft's close-up data, creating a 360-degree view of Saturn's storms impossible from any single vantage point. But perhaps the most surprising impact lies in education. When amateurs share their findings, whether through social media threads or citizen science projects like Zooniverse, they're not just contributing data, they're mentoring the next generation of scientists. A teenager analyzing Saturn's ring shadows in her bedroom today might be the mission specialist designing instruments for the next ring probe tomorrow. The lines between professional and amateur blur where curiosity thrives, proving that you don't need a space agency badge to leave your mark on the cosmos. The rings themselves seem to reward this vigilance. In 2009, amateurs tracking Saturn's equinox, when the sun crosses the ring plane, captured vertical structures casting shadows like towering skyscrapers, a phenomenon later confirmed by Cassini. These weren't blurry anomalies, they were crisp, measurable features, proof that modest equipment paired with patient observation can unveil cosmic secrets. The universe doesn't discriminate between a $10,000 eyepiece and a $10 million spectrograph. It reveals its wonders to anyone who knows how to look. And that's the real lesson here. Planetary rings aren't just subjects for elite research. They're a shared frontier where a teacher in Buenos Aires, a retiree in Oslo, and a student in Mumbai can all contribute to unraveling the same mysteries that captivated Galileo. Every logged observation, every uploaded image, is a stitch in the tapestry of our understanding, a reminder that science isn't just about lone geniuses under domes, but about countless eyes turned skyward, connected by wonder and the relentless pursuit of what lies just beyond the visible. Predicting cosmic storms in planetary rings is no longer science fiction, it's becoming a reality, thanks to cutting-edge models that blend celestial mechanics with artificial intelligence. Picture this: just as meteorologists track low-pressure systems to forecast rain, scientists now analyze gravitational resonances and electromagnetic fluctuations to predict where and when turbulence will erupt in Saturn's rings. These aren't vague guesses, they're precise calculations powered by decades of data from missions like Cassini and fed into algorithms that simulate millions of particle interactions. One such model, developed at the University of Colorado, can anticipate spiral density waves months before they form, pinpointing their origin to the gravitational nudge of a specific moon. Another, from JPL, focuses on spoke features, those enigmatic radial streaks, using solar wind data to forecast their appearance with startling accuracy. The stakes are higher than mere curiosity. For future missions like ESA's JUICE or NASA Dragonfly, storm predictions could mean the difference between groundbreaking discoveries and catastrophic collisions. Imagine a probe threading through Saturn's rings, its path adjusted in real time to avoid a brewing electrostatic storm that could fry its instruments. Or consider the value of timing observations. A spacecraft might delay a fly-by by hours to catch the birth of a propeller feature, capturing data that reveals how moonlets sculpt their surroundings. This isn't just about avoiding danger. It's about seizing opportunities, turning chaotic environments into navigable laboratories. What makes these models so revolutionary is their adaptability. Unlike static maps of ring structures, they evolve, incorporating fresh data from telescopes and spacecraft to refine their forecasts. When amateurs spot a sudden brightening in Saturn's F-ring, that observation gets fed into the system, tweaking predictions like a weather app updating for a sudden cold front. Machine learning plays a pivotal role here, spotting patterns in vast datasets that human analysts might miss, like the subtle link between Saturn's auroras and spoke activity, or how Uranus's tilted magnetic field triggers asymmetrical storms in its dark rings. Yet challenges remain. Ring storms are fiendishly complex, influenced by variables from solar radiation to micrometeoroid impacts. A model might predict a gap's formation perfectly, only to miss the way charged dust alters its edges. That's why scientists are turning to ensemble forecasting, running multiple simulations with slightly different starting conditions, a technique borrowed from terrestrial meteorology. The goal isn't perfection but probability. Instead of claiming a storm will form, the models might calculate a 70% chance, giving mission planners nuanced options. The implications stretch beyond our solar system. If we can forecast storms in Saturn's rings, could we do the same for protoplanetary disks around young stars, predicting where planets might coalesce? Or anticipate turbulence in the debris disks of exoplanets, guiding future telescopes to the most revealing moments? This isn't just about avoiding hazards, it's about decoding the universal language of chaos and order, one prediction at a time. The dawn of storm forecasting marks a paradigm shift in how we explore. No longer passive observers, we're becoming active participants in the ring's dynamics, using foresight to navigate their invisible tempests. And as these models grow sharper, they promise something even greater, not just understanding the cosmos, but learning to dance with its rhythms. Cosmic storms in planetary rings are more than just disturbances, they are master sculptors, crafting invisible artworks on a cosmic scale. These tempests don't rage with thunder or lightning, they unfold silently, their power measured in the delicate rearrangements of ice and dust over centuries. From the sprawling spiral waves that coil like galactic arms to the fleeting propeller features carved by unseen moonlets, every disturbance tells a story. It's a story of gravity's patience, magnetism's subtle touch, and the chaos that somehow births precision. The rings are alive with motion, a canvas where forces we're still learning to name paint ephemeral masterpieces visible only to those who know how to look. What makes these storms so extraordinary isn't just their scale, it's their impermanence. A gap carved by a moon's gravity might persist for millennia, while a dust-driven storm vanishes in days, leaving no trace behind. This tension between the eternal and the fleeting mirrors the universe itself, where even the grandest structures are works in progress. Saturn's rings, for all their grandeur, might be younger than the dinosaurs, and they're already fading, their materials slowly succumbing to ring rain. Yet within that brief window, cosmic storms have sculpted wonders that defy imagination. Razor-thin gaps, ripples taller than mountains, and waves that propagate like whispers across the void. Every storm we uncover adds a new layer to our understanding. The spokes that flicker across Saturn's B ring reveal the hidden dance between dust and magnetic fields. The kinked edges of Uranus's rings betray the chaos of its lopsided magnetosphere. Even the faintest arcs around Neptune whisper secrets about the delicate balance between moons and debris. These aren't just puzzles to solve, they're reminders of how much we still don't know. For every spiral wave we decode, there are countless disturbances waiting to be discovered, each one a clue to the forces shaping not just rings but planets, stars, and galaxies beyond. The beauty of these storms lies in their universality. The same physics that sculpts Saturn's rings likely plays out in the debris disks around young stars, where planets are born, or in the distant exorings we've yet to find. When we study cosmic storms, we're not just exploring Saturn or Jupiter, we're glimpsing a fundamental language of the cosmos, spoken in gravity, magnetism, and motion. It's a language that transcends our solar system, connecting the tiniest ring particle to the grandest spiral galaxy. As we continue to explore, missions like JUICE and Dragonfly will peel back even more layers, revealing storms and structures we can't yet imagine. But the real adventure isn't just in the discoveries ahead, it's in the collective journey of curiosity. Whether you're a scientist analyzing data, an amateur astronomer spotting a rare spoke, or a viewer marveling at Cassini's images, you're part of this story. The cosmos doesn't belong to any one person. It's a shared gallery filled with wonders that inspire, challenge, and humble us. So let's keep looking up, not just with telescopes but with open minds. The next time you see Saturn's rings through a telescope or a spacecraft image, remember, you're not just seeing ice and dust, you're witnessing an eternal dance of chaos and creation, where invisible storms sculpt beauty on a scale beyond human reckoning. And who knows, the next great discovery might come from your own curiosity. After all, the universe doesn't reveal its secrets to the indifferent. It rewards those who dare to wonder. What's your favorite ring storm or cosmic phenomenon? Drop your thoughts in the comments below. I'd love to hear which mysteries of the cosmos captivate you most. And if you're hungry for more deep dives into space's hidden wonders, don't forget to subscribe and hit the bell so you never miss an exploration. Until next time, keep your eyes on the skies. The universe is always